Morning, everybody. I'm Zenon Shepherd from Resolution Magazine. I'd like to welcome you all to our one-day extravaganza. Thank you for braving the weather, which presumably means that you thought it was worthwhile to find about your audio networking future, which is going to affect us all. We've got a top team of presenters and subject coverers today, and our man in charge, who you'll know a lot better by the end of today, is Mark Yonge. So I'll hand you over to him to take over from here. Thank you very much. Hope you enjoy your day.
Thank you, Zen. Well, today promises to be very interesting. We're going to have two sessions this morning. I'm going to start off with an introduction to the topic, and we then have a number of speakers, and we'll finish the morning with a panel session where you can quiz us to your heart's content. I'm primarily a sound engineer. I've been working in sound for quite a long time now. More recently, I've been working in standards, which has given me an interesting and orthogonal look at the way that technology evolves and gets used. But we'll come to that perhaps later. And this forum is slightly ironical because in the year 2000, 14 years ago, the AES organised a London conference called Moving Audio, and I chaired it. And it was all about how to move sound from A to B on networks. And at the time, that was quite a new and novel idea. And we had a very interesting two-day session on how you might do that and what you might achieve. And then it sort of all went quiet for a bit. But there's been lots happening since then, as you all know. Now, primarily, when we talk about audio networks, this is going to be about network audio streams. We're not going to be talking about file exchange, because that's pretty much a known art. We're talking about streaming audio. And we're not talking about voice over IP. We're not talking about streaming music. We're talking about production-grade audio, and I take that to mean linear PCM coding. It's got to be 48 kilohertz or thereabout sampling frequency, 24 bits typically or better. And that's the basic working tool for all of us in broadcast and in music production and in live sound. Mono to multiple channels is a given. Now, there really are two audiences for this, and I noticed, looking at the delegate list, that we have one of those audiences here today. Can I just quickly ask, how many of you are working in sound operations directly? A few. How many of you basically consider yourself to be working in sound in a more general sense? That's a majority. How many of you are working in IT in a general sense? Welcome. Because there are two audiences. There's audio engineers who need to understand that in the network future, and I believe there will be a network future, the infrastructure that you use will no longer be under your control. You're going to need to talk to IT people and have a meaningful conversation. Part of what this requires is a common language, and at the moment I'm not convinced there is one, but we need to work towards that. And then IT engineers. IT engineers typically work in commercial IT applications, and they tend to have different understanding about what now means when in a broadcasting sense. These two groups urgently need to work together, and we're seeing now that they are, but there needs to be more of it. This is, of course, about digital audio. There's no sense in talking about analog audio and networking. Computers have been around for ages. They're commodity items. They're used for disk storage, for recording and playback and editing. And they use bus systems, quite limited size. But they've been around for 20 years. Digital streams are different. Up to now, they've used dedicated streams with dedicated cabling, using AES3 for 2-channel streams, or MADI for multi-channel streams. But there's a bit of a problem with this. And the problem is this. It uses special cable, and it uses special connectors. And the cable is bulky and rigid, and the connectors are really quite expensive to install. Here's my friend John Schmidt showing off a bit of an installation at ABC in New York. This was taken about 6 or 7 years ago and shows fixed cabling for audio and video for ABC. And a lot of broadcast stations will remember this as the way it used to be. It takes years to specify and install, and once it's installed, it's rigid. You can't really change it very quickly. And that's not really the way many broadcast and other businesses work these days. So, why networking? The answer by now should be obvious. You want the same benefits that commercial IT had when networks were installed there. It's a shared resource. It's a generalized infrastructure. That means you can put in the cabling and the connections and work out what they're going to do later to a large extent. It's comparatively simple and quick to install. It's comparatively simple and quick to adapt as the business needs change. And that's a big issue, because when you start a new business or a new venture within an existing business, you probably can't guarantee how it's going to work out in 3 to 5 years. So, if we want the benefits of scale and generalized infrastructure that the commercial IT people had, what's different with audio? Well, the network is going to need to be transparent under all conditions, and there are going to be delays, and you're going to have to manage them. Those are the two headline issues. Now, I am not going to get too involved in technology here because I think that's inappropriate. But you'll all be familiar with the 7 network layers that people use to describe what they do. And that's at the bottom of this diagram, the OSI network layers, from the physical layer, which is the wire, up to the application layer that speaks to what's going on inside your computer. There are layers above that we've used for years, but we haven't thought of them as layers. Right at the very top is the important one, and I'm going to come back to that. Second layer down is the electroacoustic and analog layer. Once upon a time, this was all there was. There was the electroacoustic analog layer, and there was the physical layer, and that was all there was. And life was simple-ish. But that takes you from a microphone signal, for example, through to a loudspeaker signal, so your audience can hear what you're doing. In digital audio, you have conversion, so you have an analog to digital conversion at the front end. Data moves to a digital to analog conversion at the back end to feed the electroacoustic analog layer there. And sometimes, if you need to use it, there'll be a codec. You may need to use data compression coders and encoders and decoders. So that's 4 purely audio layers on top of the 7 classic network layers. The one at the top I want to come back to, the performance to experience layer. This is actually what we're delivering to our audience. There'll be a performance that you're capturing, and then it goes through all of this technology, and at the end it needs to be presented in a way that is meaningful to that audience. And unless that bit works, the rest of it is meaningless. So that layer right at the top, from performance to experience, I call the value layer, because that gives meaning to the rest of it. Are we nearly there yet? Yes, I think we are. And we're going to pick that up in some detail in the rest of today. So, let's move on and talk a bit about audio networking. Networks themselves are not new. Here's a bit of history for context. I'm not going to labour this, but I think it's useful to see what happened when as a run-up to where we are now. In order for streaming to work at all, of course, the technology needed to ramp up from a very low level to a point where it could handle the speeds and capacities that we need. And you'll see that as we go through. And Moore's law, bless it, has helped in networking as it has in disk storage and in semiconductor memory and all those other areas. First networking, arguably, was the telephone. It also introduced us to the idea of network benefits. This is network used in a slightly different context. Network benefits mean that if you have one phone, that's useless. If you have two phones, you can sustain a conversation, and that's beginning to be useful. If you have 10 phones and you can speak to any of them, now that's much more useful again. And you'll find that as you increase the number of nodes on a telephone network, the utility of each phone increases geometrically. And that's quite cool. This was demonstrated by Bell and all of their spin-off companies in the late 1800s, early 1900s, to a point where we now take it entirely for granted that telephones are all over the place, we can make calls, and we all benefit thereby. For computer networking for data, that came much later. There was time sharing of server-client style of time sharing in the 1960s. In the 1970s, the US Department of Defense introduced ARPANET and encouraged people to find ways of using it. In 76, Ethernet was first described. 79, the OSI network model was described, setting out in general terms how networks ought to work in a perfect world. At that time, it wasn't a perfect world. 83 is an interesting watershed because the US Department of Defense decided that ARPANET was really interesting, but the military didn't want to use it. They had another system, so ARPANET could now be civilian, and it became available. In 84, Ethernet was standardized as IEEE 802.3. And more significantly, a year later, IBM PCs showed up with network cards in the back with Ethernet. And for many of us, this was the first time we'd seen a real network and started to think about the possibilities. Because the IBM PC went all over the place, and suddenly it was the way computing was done. World Wide Web came in the 90s, mid-90s. Fast Ethernet took the basic speed on the network up to 100 megabits per second, and now it looks like we have enough speed to do something interesting with for audio. And so it came to pass. 1997, CobraNet introduced audio over an Ethernet system. Gigabit Ethernet in 1999, 2001, EtherSound. Now, what was sort of interesting for me at the time is that even though there were these systems for audio over Ethernet, The accepted wisdom at that time was that there was another group of players who were going to dominate the long term, and that was the telecoms companies. And so when you read a book like this, which I bought in 1998 in Atlanta, it's a US government paper on standardization for networks, and it assumes that media networking is going to follow telecom standards, and ATM was the way of the future. And so in 2002, the AES standardized digital audio over ATM networks, which worked very well, but arrived just in time to be undermined by the fact that the telecoms companies moved their systems from the synchronous digital hierarchy to something that looks much more like IP, but I'm going to come back to that. Since then, we've seen Axia Livewire introduced, Ravenna introduced, Dante introduced. The EBU, realizing that ISDN was going away, introduced something called audio contribution over IP and updated it in 2012 in cooperation with the AES. And in 2013, the AES 67 standard was published, which was a result of that cooperation. Now, in the early days of media networks, there were lots of alternatives. There were lots of proprietary systems, many of which we no longer know about. Of the standardized systems, Ethernet is the obvious one that survived. Token Ring was promoted by IBM and Token Bus by others. There was private venture networks from Novell and ArcNet, all of whom have basically disappeared. So there's only Ethernet really surviving. The early systems were slow, barely useful for file exchange. Telecoms had speed, but it was difficult to use. And this was the point I was making, that the commercial IT people captured telecoms, not the other way around. And why was that? Lots of reasons. Ethernet and TCP/IP that drives the IP standard was solidly standardized, could be demonstrated working all over the place. There was lots of equipment, and the equipment wasn't that expensive. And offices were putting it in huge quantities. And there was a base of technical support that understood how it all worked. So it all came together quite nicely. Now, my interest is in standards, and it's useful to see who's driving this bus. We have, at the top of the tree, we have international standards from the IEC, ISO and IEC. We also have some standards for telecoms from the ITU. They're all worth paying attention to. At the next level, we have industry standards from IEEE in the States. The Internet Engineering Task Force, which started out as a little volunteer body and has grown to be very important indeed. And they have a big stake in the way that TCP/IP works. Can't ignore them. And the World Wide Web Consortium, W3C, is also relevant. These are all working with commercial data networks. When we come to looking at the media industries, I'm aware of two organizations producing standards. There's the Audio Engineering Society, who I work for, and the SMPTE, who we cooperate with. Now, let's just talk a little bit about computer networks to give some shape to what we're talking about. What's a network? Well, the simplest thing is a bus, which you connect units together in a chain, and it's the way that most laptop and desktop systems work, and the bus can be quite simple or it can be quite sophisticated. IEEE 1394 Firewire is moderately sophisticated. Thunderbolt is quite sophisticated, but they're all bus structures, and they can only get so big before the bus no longer supports the traffic. Local area networks is what we use in our offices, and it consists of twisted pair cables connected by switches to connect lots of units together, whose function is determined by the configuration of that network. And if you take a typical long cable run to be about 100 meters, the diameter of the whole LAN is in the order of 200 meters or thereabouts. It's good enough for a building. When you want more than the building, you have to think about cabling that's a little more capable than twisted pair copper wire. And you can think in terms of local area networks connected together by a backbone, probably a fibre backbone, because they can carry data comparatively long distances. Now, the size of this can vary enormously. About a 5 kilometre diameter, it's not unreasonable. It could be larger or smaller. My understanding in this area is not encyclopedic. Then there's the wide area network. Now, wide area networks are distinguished by the fact that at some point you have to give your data to a telecoms company to ship it long distance. And they will probably modulate that signal onto a carrier and put it on fabric that you don't know about, and ship it to somewhere else and have it show up and continue in a LAN somewhere else. The system we know best is the internet, because that is all over the place, but the internet is not yet up to carrying professional production-grade audio streams. It's just too complicated at the moment. But we're moving in that direction, so we need to keep our eye on that as a goal. So what about the audio? Well, it's digital, and provided the bits get from A to B, the waveform quality is not the issue. The timing quality is the issue. Now, many of you will have seen John Watkinson's excellent article in this month's resolution, plug, and it's all good stuff. And John makes the point that there is no such thing as real time in a network. I would go further. I'd say there's no such real time in digital audio. I tried to look up the meaning of the word real time, because in standards the words are important and you need to know what they mean. So I said, let's find out what real time means. And I came to the conclusion that nobody knows. I looked up in the IEC International Electrotechnical Vocabulary, which is a free online resource if you can't sleep at night. And this is the best definition I've been able to find. Pertaining to the processing of data by a computer in connection with another process outside the computer, according to time requirements imposed by the outside process. I don't think they know either. Does this mean now? The word real-time needs to be pinned down and established. In a network system and in a digital audio system, it will never mean exactly this instant, because there are delays throughout the whole chain. And it's probably useful to pick up and see where those delays are right now. Analog systems have no storage. Analog systems have no delay apart from the speed of the signal going down the wire. So we never had to think about it. In years and years and years of analog technology, you never thought about time delays. That was a video problem. Digital conversion gives you a delay of about 20 samples, or about a millisecond in the ADC, and another millisecond in the digital to analog converter. So that's about 2 milliseconds delay right there, simply from the decision of converting to digital audio. Now, that figure will vary. There are strategies to make that longer and shorter, but the vast majority of converters use oversampling techniques these days, and they use time in their architecture in order to simplify the filtering. And so you get this delay. It's always there. It's kind of neat if you can have the same delay in all the channels of a stereo signal or a surround signal. But there will always be a delay. The next stage is when you have a digital to digital connection. There'll be another delay, because as typically, when you take a digital signal and put it into another box with a digital signal inside that, you resynchronize the incoming digital signal to match your internal media clocks. And you tend to lose a sample. If you're going to use data compression codecs, now you're looking about delay in large wholesale amounts. There are digital codecs, data compression codecs with very short delays in the order of 2 milliseconds. Some of them go up to 200 or 300 or 400 milliseconds on the basis that the more delay you put into the encoder and decoder, the more sophisticated you can make it, and the more efficient the coding can be, so you can get more audio into less bandwidth of data. But you really pay for that in time. Sampling frequency conversion is not cost-free. If you have a CD playing digitally into a broadcast chain, it arrives at 44.1, you convert it to 48 kilohertz sampling frequency. That also uses an oversampling technique, and you also lose another millisecond there. And so this speaks to something that I've talked about for years, which is our forefathers worried about wow and flutter and distortion and tape artifacts and horrible stuff like that. And that's all gone away because it's digital. But we now have time artifacts, and we're not thinking about those very clearly. And here's the news. Networks are going to add more delay. They're not going to make anything shorter. We've got to be grown up about this. There are two major sources of network delay. First is in the packetization. In all networks, you take the data and you put it into a packet, and then you ship the packet to somewhere else, and then you unpack it and then play the data. If you have a small packet with very few samples in, it's quick to load and it's quick to unload. And so the packetization delay can be short. Typically in a 6-sample packet, the packetization delay is in the order of 125 microseconds, which is fairly brisk. If you want a little more efficiency, you'll be looking at about a millisecond. If you want a lot of efficiency, and the EBU ASIP uses 4 milliseconds, that's what you get. The 10 milliseconds I've written down here is a bit extreme. I actually don't know of a system that runs all the way up to 10 milliseconds, but I can imagine applications where that might be attractive. But that's right on the fringe of what we're talking about here. The next source of delay is in the uncertainty with which the packets arrive at the destination. And this is called packet jitter. If the packets instead of arriving at a steady rate, arrive in a lumpy fashion, because they get clustered up in switches at some point in the network. You have to make the buffer at the receive side big enough to handle the worst case arrival. And so in a network, perhaps a very busy network, where packet arrival is quite lumpy, you may need a longer buffer to handle that packet jitter. It's worth pointing out that network people will talk about this as simply jitter. For audio people, I need to point out this is simply one part of jitter and has nothing to do with the sort of jitter we talk about in converters, which is completely different. How do our colleagues in SMPTE look at this? Well, they have exactly the same problems, although they're handling much greater bandwidth. The delay values come out differently because the compromises in the stream delivery are different. There is a lip sync conundrum which has been unfixed for nearly 20 years. But in the networked world, there is a possibility that we might be able to fix that old lip sync problem. And this comes to a consideration of media clocks. Since the dawn of digital time, it's been necessary to synchronize media clocks using a distributed sync pulse system. Whether you use distributed video syncs, or word clock, or AES 11 sync signals, you needed to send a wire to every box to say now at the beginning of every clock edge. And so you had the same problem of hardwired cabling, and it's a nightmare. But how about if you could distribute time information to all of these boxes with sufficient care and precision that you could generate your own media clocks and they'd be in harmony with all the other media clocks in the system? Wouldn't that be neat? Let me introduce you to IEEE 1588-2008. It trips off the tongue, but it's a very significant document. This is for precision time protocol, and depending on the way it's implemented, it can give you time down to nanosecond precision in your network. And it's distributed over the network itself. It does not need extra cabling for sync pulses. This is a big change. This is what makes, in my view, this is what makes audio over networks possible, because it means you can get all the benefits of the simpler fabric and still keep your media clocks coherent. Going back to what I was saying earlier, it also promises that there's a way of identifying times within video and audio streams such that you can realign them at playout and fix the lip sync problem. That doesn't happen yet, but it's something we're working towards. Multi-channel streams, I don't need to tell you this. If you have a 5.1 signal, you probably need to keep all those channels together, or you're relying on the high-quality timing at playout. That's just an obvious given. So, audio infrastructure equals IT. This is one of the futures we're looking towards. This is why we're here. Audio engineers no longer have direct control of their infrastructure, which is slightly scary. They will need to speak to IT people to come to a common understanding of what's practically needed. Knowing full well that these IT people are going to be handling all sorts of media types. There will be some installations which are audio only. I believe the general case is that most installations will be multimedia and will be handling video and lots of other stream types as well. So there's a need for media-capable IT engineers, and that's one of the messages I'd like to put into your minds, which is there's There's a hybrid type of person who really understands the network system and knows how to configure it with confidence and understands why that's important. And when I spoke with the EBU in Geneva earlier this year, they saw that as a key part of rolling out our network future. Remember the value layer. That's the bit that's important. That's why IT people and audio people need to work together to realise the value layer. And so, quickly to summarise, I'm not overrunning by very much. There's going to be a pressure to simplify technical installations. The success will depend on system specifiers, and that may well be you. Networks from where they are now will increase in size and complexity. That's obvious. And IP network implementations will evolve to get smarter and more elaborate. We should also be aware that new network types may evolve in the future, but they will tend to pick up on the working principles that we establish now. And LAN shall speak unto LAN. In the future, we will all be networked. Thank you very much indeed.